talk about post-quantum. Everybody is talking about artificial intelligence and how it will change the world. But the new computers that the folks are trying to build with quantum technology, it might also change a bit the current computing thing that we are knowing. I'm Cyril Leclerc. I work at Dashlane. Dashlane is a credential manager. It helps people to manage their password, their credential. Now we are trying to implement passkey. I don't know if you have heard about that. And we try to do that in a simple and secure way for personal use and also for professional use. Let's start with what is a quantum computer. A quantum computer, unlike traditional computers, they rely on specific mechanism and specific behavior of subatomic particles. Traditional transistors do that also, but quantum computers are using other properties of the matter. I won't explain exactly because I don't know. I'm a security guy, I'm not a physicist. But the main thing I have understood is that quantum computers are able to handle the information in a very different way than the classical computers. Where the classical computers are using transistors that are able to understand 1 and 0, the quantum computers are able to represent and use both 0 and 1 simultaneously. They call that superposition, and that's really the main fundamental thing of the quantum computer that make them special and able to deal with different problems. And some of them, they are able to do it quite very, very fast. Another part of those computers, and they are really beautiful. I think they are really beautiful. They look really good. And they are built with other stuff than the classic transistor. And they call that with cool names, supraconductors, trapedions, photons, artificial or real atom or quasi-particles. And depending on the architecture, this kind of system needs to be treated really specifically. Some needs to be at almost the absolute zero. Some other will need other kind of error corrections because the real world is interfering because of the magnetism, the temperature change of everything. And yeah, it's hard to build. So that's what they are busy at. IBM, Google, Alice and Bob in France, they are trying to build those computers and to make them able to deal with more and more qubits. That's really the thing. Today, they are able to build computers with 1 or 2 or 3 or 4 or 100 qubits, something like that. But they aim for something bigger. For instance, IBM is trying to build a 1,000 qubit computer for 2024. So we've seen, usually we deal with bits, 1 and 0, and quantum computer have to deal with superposition of that. If you want, I don't know, a metaphor, what is superposition? You can imagine when you throw a stone in the water, you will generate waves. If you throw 2 stones, you will generate multiple waves. So the ability to represent those multiple waves, those superpositions, are what quantum computers are able to do. So why am I talking about quantum computer? You know why it's important about security. It's especially important for cryptography. Those 2 folks, the first one is Shor, it's an American mathematician, and the second one is Grover, it's another American mathematician, and they devised algorithms that are able to break the current encryption that we are using. The first one, Peter Shor, is able to do a new algorithm that will be able to factorize big numbers, and the factorization of big numbers is the key of the cryptography that we are using today. Grover is able to work on another thing. He's able to reverse the black box function. Black box functions are used in symmetric cryptography, AES, the one that everybody is using today, and the other one, the primes, they are used in RSA and elliptic curves, the stuff that I use also to secure the internet today. So what's happening? The things that we are using today, symmetric encryption and key exchange, RSA, elliptic curves, Diffie-Hellman, and these kind of things, the things that are powering TLS, HTTPS, and everything we are using today, they are vulnerable to the Shor thing. So what does that mean? Is that if we are able to build this computer in the next years, it will be able to break this encryption, and this encryption is but it's fundamental. It's fundamental for everything on internet: payments, security, confidentiality of what we do, and so that's really important. Another part that is important is that we don't expect quantum computer to be available right now, this year, or even soon, but we expect them to be available in something like, not this one, something like between 10 or 20 years. Some people are saying more. We don't know exactly, because there are a lot of stuff to fix and to be able to build such computer at scale. But yeah, the experts of the field are saying maybe in 10 days, maybe in 15 days. But the issue is the stuff that we have today. Maybe we have already stuff that we want to keep encrypted, and in 10 years. So maybe we want the things that we are using today, we want them to be secure in 10 years. That's why maybe we need to take care of that today. If we already have stuff that we want to protect, we need to already work on this one. AES, the biggest encryption, symmetric cipher that we are using, it's vulnerable if you are using the old one, the AES 128, but it's not vulnerable if you are using the new one. So most of the framework and libraries that the developers are using should be able to use AES, but most of them won't have the ability to implement new ciphers to protect against the other attack against the asymmetrical keys. So the store and now and decrypt later, yeah, that's the thing that maybe some people are afraid. We can maybe guess that some agencies or government are already trying to stash a lot of data. And so when they are able to have this computer, they will be able to decrypt it. I've heard that even in France, the government is trying to build a computer and is doing some appel d'offres to get it done. That's why it's a threat today and not only in 25 years or something like that. My mic. Okay, so I've told you IBM is already working on a 1,000 qubits for next year. So we'll see if they're able to do it and what we will do. So what now? The NIST, I don't know if you know this organization, it's an American one. They are working on standardization of many things, and although cryptography, and they have decided that it's the moment to take care of that topic, and we want to, we are looking at what they are doing. They should announce some winners this year, but we already have a lot of implementation and things that we can work on, and so yeah, it probably won't be the final ones. Maybe we will have to wait some years again to have something usable and final, but it's moving. For TLS, TLS 1.3 is implementing hybrid cryptography, so they are able to use multiple key exchange algorithm, and they will include a classical one and a post-quantum one. And that's a good thing. So I have put some names in the slide. So you will have to use different ciphers to implement the new crypto. And yeah, there is especially two hard problems that are used by those crypto. The first one is lattice with error. And I won't explain it right now, but the idea is from the previous one, the mathematical hard problem was about factoring number or doing stuff for logarithm. And for the new one, it will be solving new problems, one about lattice. And yeah, that's the idea. We don't really need to understand that. That's a mathematician thing, but we need perhaps to know which one we will have to use and which one we will use. So how to do that? We have started to do that at Dashlane. We have done that previously because we have to change the cryptography of our stuff. And the idea was to add in the code the ability to be able to deal with multiple cryptography, the old one and the new one, and be able to switch when we need that. So if you want to prepare for the post-quantum world, you have to first be able to be agile. It means that you'll be able to change your crypto because you will need to re-encrypt the stuff of your users and so they can use it. And you will have to deal with the update cycle when the people will be able to update and this kind of thing. And yeah. And for the post-quantum world, cryptographers are really conservative folks. They don't like new things, and they want old stuff that ideally could be proved mathematically, but it's not the case for most crypto. We don't have really mathematical proof, so we hope that it's working. And so for the new thing, the idea of the cryptographer is don't use the new one. We don't know if it will be safe or not, but use the old one and the new one at the same time. And hopefully one of them will be safe enough for everybody. That's the current state of the affair. You can either do it serially, you first encrypt the first thing using the old algorithm, and the new thing, and you re-encrypt with the new algorithm, or you can do in parallel and then use the hash function then to gather the encryption key. So what about you and what you should do today? You probably can not care and you can learn a bit more about it, because I don't know if it will come really fast or if we will have a lot of time to deal with it. But if one day someone is able to have a computer and break RSA, it will be a huge mess if we are not prepared and if we are waiting too much, because the mechanism that we have to update our cryptography is also relying on this kind of cryptography. So if you, yeah, it's a chicken and egg thing. If you are not starting soon enough, yeah, we won't be able to do it. At Dashlane, it was simple. We are a simple software, but it has been at least 2 years to be able to migrate from one crypto to the other one. So you want to start quite soon if you want it to work. I have put some references here, so you can have a look if you want to look at what we have done. And we have not shipped anything post-quantum yet. We are working, and maybe this year or next year we will ship a post-quantum ready credential manager, so everybody is able to use it. And that's all. Thanks for listening.